Hello there. Thanks for joining us on Space Nuts, where we talk astronomy and space science and sometimes canines. And coming up in this episode, does anybody really know what time it is on Mars? Well, apparently they've worked out a way, and it's really fascinating. And there's a good reason for it, too. We're also going to talk about the weird orbit of TOI 3884b. I was only there last week. And chewing gum on asteroids. It's a thing. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again for more. Here's Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Complete with the dog.
Yes. Good old Geordie. He's great value. I still laugh at the way he greeted us when we went to your place a month or so back, and came tearing down the stairs.
That's right. That's it. But that's his
Modus operandi.
Yes, it is, and it's not aggressive. It's just
Excited.
hello, how are you? But it just goes beside himself when. Anyway, he's already had a session this morning, standing at the bottom of our stairs, yelling at something, and I've no idea what it was.
Probably a blade of grass that got blown in the wind.
Yeah, that's the level at which he gets excited. Absolutely. Oh, blade of grass. Whoa, whoa, whoa.
Yeah, I love it. Okay, we have got some really interesting topics today. We've always got interesting topics, but this is a really great combination. We're talking time, weird orbits, and chewing gum. Let's start on Mars. And to quote the famous song, does anybody really know what time it is? Mars is a bit of a problem when it comes to time, and so is the Moon to a certain degree, because time doesn't run the same way in those places as it does on Earth. And going forward, that could become an issue because we're going to ultimately spend time on Mars, wandering around growing potatoes. But we need to be able to get the time right.
We do. And I mean, there are some sort of basic facts before you get into the nitty gritty, which include the fact that a day on Mars is 40 minutes longer than a day on Earth.
Yep.
So about 24 hours and 40 minutes. And of course, a year on Mars is longer too. It's 600 and something days of our days. 687 is the length of time a Martian year takes. So they're the easy bits. They're the givens. But if you're trying to synchronize your clocks between Earth and Mars, and this is kind of already happening with the rovers, the fact that the rovers are actually controlled from Earth, but because of the time delay for signals to get to Mars, they actually there's a degree of autonomy in all the rovers that are roving on Mars. That's not the issue at the moment. The issue is how you make your clocks on Earth agree with clocks on Mars. And there's two subtleties that come into this. And I should credit the organization that's done the work on this, which is the United States National Institute of Standards and Technology, or NIST. They've actually done detailed calculations about exactly how time varies on Mars. And so you've got two things, Andrew, when you're trying to synchronize with clocks on Earth, apart from the time, the time delay with signals going to Mars. The two things that come into being, both are to do with Einstein's theories of relativity. And we've talked about these ad infinitum. We've gone on about them a lot for a long time. And you, from that, will know that when you put a clock into a gravitational field, it runs slower. And that's the time dilation effect of general relativity. So we know that clocks on the surface of the Earth run slightly slower than clocks either in space or even in the air. We've now got clocks that are so accurate you can tell the difference between time ticking away on a jet plane at 10 kilometers high and time ticking away on the surface of the Earth. But Mars, of course, also has a gravitational field. It's got a gravitational pull, but it's only a sixth or thereabouts of what we have here on our planet. So that means because the gravity is lower, a clock runs faster on the surface of Mars. If you're on Mars, your clock is ticking away at the same rate, but to an outside observer, it runs slower, and to an observer on the Earth, whose clocks are running even slower, it seems to be running faster. And the calculation has been that from the NIST, the National Institute of Standards and Technology, a clock on Mars would run 477 microseconds faster per day compared with a clock on the Earth. So 477 millionths of a second doesn't actually sound much, except that when you've got communications like the 5G network, you're working to, the internal clocks work to better than a millionth of a second. And so 477 of those millionths of a second is it's throwing
messy.
Communications out. Very messy indeed. But it actually gets messier because, as you know, we've talked about this too, the special theory of relativity says that if you have a clock on a moving object and you observe it from not a moving object, then you will also get time dilation. That clock will look as though it's going slower, even though it's ticking away at the same rate to the person who's on the moving object. To an outside observer who's stationary, it looks as though it's going slower. And so we've got an effect because of the motion of Mars relative to the motion of Earth. Now, Mars is in an orbit around the sun, just like we are, but it's actually quite an eccentric orbit. In other words, it's rather elongated, more so than Earth's orbit is. And so that means it's always got a motion towards or away from the Earth. And that adds another uncertainty, and which can go either way, because if it's coming towards us, then you get a different effect. It's 226 microseconds, the daily offset in the course of a Martian year, the difference between us and there. I just said something that I want to correct there, because it's the thing is always the same sign. It doesn't matter whether it's going towards us or away from us. You've still got the offset in terms of the relativistic time dilation, which is not what I said. So I'm correcting that now. But yeah, so you've got this additional 226 microseconds. So 477 microseconds with up to 226 microseconds added to that. It means you've got actually quite a messy difference in time. It's almost a thousandth of a second.
Yeah. This relates to a time where we've got long-term human presence on Mars, and we need to, and the technology doesn't exist yet, but we need to be able to communicate with Earth in real time. Technically, they're going to probably develop ways of setting up communication systems so that the radio signal issue doesn't impinge on that communication. Because at the moment, it's like 24 minutes to send in.
I think at maximum it can be, and it's you're not going to be able to get away from that, but you can build that in because you know Mars's distance very precisely. So you can build in a time delay.
So this is more about working out a time system that is in sync with Earth. It's not. Does that mean we have to invent a new kind of clock to use on Mars so that it's?
I think what it means, it's really about the internal consistency of time signals on Mars. So you've got you're absolutely right. The synchronization with Earth comes into play here, but you also want to make sure that your communications actually on Mars, which would be vital, are all right, and that's in a way okay, because the relativistic effects don't come in there, because you're all in the same gravity and you're all basically moving on a planet at the same speed. It's like we don't have to take these effects into consideration when we're talking between ourselves on the surface of the Earth. It's only when you're talking up to satellites above the Earth, which we do through GPS and through communications, then you need to take those minute time differences into account. And in a sense, that's what this is all about. So, you've got the basic property that you can't get away from, the speed of light, 300,000 kilometers per second. That's the speed at which radio signals go to and from Mars. That you can deal with because we know the distance. But then on top of that, you've got this added tweak in terms of synchronizing our clocks with the clocks on Mars, which makes for a very interesting, scenario.
Yeah. Well, here's a dumb question. Why can't we just do what we do on Earth across the entire solar system and use Zulu time? Would that not work? It's just Zulu time on Earth basically means it's the same time everywhere on the planet.
That's an expression I haven't heard before, actually.
Oh, it's a real thing.
Is it?
Zulu time, yeah. It's used by the military specifically. But
yeah, that might be why I haven't heard of it.
I'll look it up because right now it's set on Greenwich Mean Time, but Zulu time applies across the entire planet. So,
but that's what we would call universal time.
Same
in
thing.
the world of astronomy.
Yeah. So why can't we do that?
Well, we do. I mean, we do in space, but that's fine. That gives you a time base, but you've got to tweak it for all these relativistic differences.
So you've got the time slip problem regardless of how you run the clock.
It doesn't matter how you run the clock. Yeah. So on, if you're on one of the moons of Uranus, then you'd probably still work on universal time or Zulu time, when you synchronize that with Earth, you've got to take all these things into consideration. That's the bottom line.
Okay, I get it. Gosh, it's so complicated. And yet, Mars is as close to Earth as you're probably going to find in another planet. The daytime difference is only 40 minutes. But when we actually set up long-term stays on Mars, that in itself is going to be a problem for humans because we are tuned to our own environment.
For us, yeah.
Having an extra 40 minutes a day is going to throw everything into a spin. Yeah. And I think we talked about this some time ago, and the only way around it would be you'd have to have a daytime snooze.
Well, we kind of know about this already because, and again, we've talked about this before, that the people who actually operate Perseverance and Curiosity and all the other rovers that are on Mars, the ones that the only other one that's operational is the Chinese one. The people who operate those actually change onto a 24 hours and 40-minute schedule. So they're isolated in a sense from their community, and I think they quite quickly adapt. I think it's a bit rough for the first few days. It's a bit like jet lag, but I think they quite quickly adapt to that longer day, a Martian day.
So if you start work at 9 o'clock on a Monday, you start at 9:40 on Tuesday. Is that?
Yeah, that's right.
Blimey! By the end of the week, you've.
Yeah, so actually it's the other way around, isn't it?
Would it be? Yeah, you'd have to start earlier.
By Monday, well,
it's the same as trying to figure out daylight saving, isn't it? Yeah. Just, am I going to be early or late? Imagine trying to do that every day. Gosh, no, it's fascinating, and the bottom line is this team has more or less figured it all out and worked out what we have to do to make the time right when we get to Mars.
You're right. And you were right, actually. You would start. So to everybody else, your day, you'd be starting 40 minutes late Tuesday. But you're still starting at midnight or, whatever time you started, 9 o'clock, in fact. 9 o'clock Martian time.
Yeah. It's just a bit crazy, isn't it? But it's a fascinating story. If you'd like to read about it, it's on the website SciTech Daily, or you can read the paper that's been published in the Astronomical Journal. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a break from the show to tell you about our sponsor, Antigravity A1. Have you ever wished you could actually feel what it's like to fly? Not just control a drone from the ground, but truly experience the air around you. Well, that future has just arrived. Introducing the Antigravity A1, the world's first all-in-one 8K 360 drone. And it's officially available now. This isn't just another drone. It's an entirely new category. With Antigravity A1, You don't fly by fiddling with sticks. You fly with your hands and your head. The vision goggles use ultra-sharp dual micro OLED displays, and the grip controller's free motion lets you literally point where you want to go. Look left, the drone looks left. Tilt your hand, it responds instantly. It's the most intuitive flight system ever created, easy for beginners, but still offering full FPV controls for seasoned pilots. The Antigravity A1 is now available in 3 bundles at the Antigravity store, Best Buy and authorised retailers worldwide. So if you ever wanted to rethink what a drone can be or what flight can feel like, check out the Antigravity A1. Just visit antigravity.tech. That's antigravity.tech for the Antigravity A1. This is a new revolution in drone and drone photography. That's antigravity.tech, or you can tap on the link in the show notes.
0G, and I feel fine.
Space Nuts.
All right, we're going to focus on a target of interest now. I only just figured out what that means. TOI 3884b. This is a planet orbiting a star, and at this point in time, they've only found this one planet. But the weird thing is, its orbit is just so out of kilter with what we would consider normal, and they don't know why.
They don't. So you're absolutely right. We're talking about an object by the name of TOI 3884b. I was just talking to a radio presenter in Coffs Harbour in northern, what's it called, the mid-north coast
Mid-North Coast, yeah.
New South Wales, about this very topic, and he wants to rename it the hula hoop.
That's a good idea.
Yeah, because as he said, with hula hoops, the problem is always keeping the hula hoop at the same angle to your waistline. He said it tends to wander off, and that's exactly what's happened with this planet. So, Luke Ryan, this is one for you.
Cool.
It's the hula hoop planet. So, what's the story? Well, this is a planet going around a red dwarf star. It's one of the 7,000 odd now exoplanets that we know about. It's at a distance of something like 130 light years from Earth. This red dwarf is pretty unspectacular in that it's just a typical red dwarf star, but it's got spots on it. Now, a lot of stars we know have spots on it, and actually here in Australia we've got a group who I work with quite often up in the University of Southern Queensland whose speciality is star spots and understanding how we can learn about them. And I've seen some of the papers that they've written, and sometimes these star spots, they're almost a quarter of the size of the disk of the star itself, unlike the sunspots that we see, which are, yes, bigger than Earth, many of them, but the Earth's 100 times smaller than the sun. So our sunspots are quite tiny compared with some of the star spots that we know exist on other stars. And this particular red dwarf has at least one big spot, which are they're cooler than the rest of the atmosphere. They're cool spots, and that's why they look darker. And it's because of that, even though you can't see the spot directly, what you can see is the way the light from that star changes as the star rotates, bringing the spot towards us, and then on the other side of the star, and when the spot's towards us, it's a little bit dimmer. And so what they've done is these scientists, and I should acknowledge where they are, I'll come to that in a minute, they have figured out, first of all, from that spot rotation, they've figured out that this star itself rotates every 11 days, which is, of course, shorter than the sun. It's kind of half the sun's rotation. But that 11 days is the key to understanding how the star itself rotates. Now, enter the planet into this. The planet itself goes round in something like 4 days. So it sort of whizzes around the parent star. But what the scientists have done is used some very, very careful measurements and a phenomenon which is called the Rossiter-McLaughlin effect. which is to do with the way the appearance of a star's spectrum changes as a planet rotates around the star or revolves around the star. And using that effect, they have basically discovered that this planet orbits the star at an angle of 62 degrees to the star's equator. And contrast that with the solar system, where the planets all orbit more or less in the same plane. Mercury is the outlier in that; it's tilted, but that plane is more or less the same as the equator of the sun.
Yeah, if you compare it to Earth, that planet's 40 degrees off. We're 23.44, and they're 60, whatever you said. That's a heck of a tilt.
No, it's a different tilt you're talking about there.
Oh.
That's the tilt of the Earth's...
Oh, that's the axis.
Rotation axis, yeah.
Right.
But the tilt of the Earth's orbit to the sun, to the sun's equator, is effectively zero.
Right, gotcha.
As most of the planets are, with the exception of
so
Mercury.
It's not the tilt, it's the actual orbit itself is...
Yep, that's right. It's the orbit itself.
That's even weirder.
Not the rotation of the planet. That's right. It's good to clarify that. Well,
yeah.
Thanks, Andrew. And that's peculiar because, we conventionally understand that the way planets form is in a what we call a protoplanetary disk, which surrounds the infant star. And because both the star and the planets have come from a collapsing cloud of dust and gas, which is itself rotating, and it's that sort of fossilized rotation that we see in the rotation of the planets, or the revolution of the planets around the sun and the rotation of the sun, and they're all in the same plane. This one's not. So how has that happened? And the suggestion is...
Oh, I know. Thea did it.
Well, it could be a Thea effect, something that's actually collided with this object. But there's apparently, as you pointed out right at the beginning, there's no other objects known to be in orbit around this star. It seems to be a single planet. That's not to say that there wasn't something that collided with it and moved its orbit. But even, something like Thea hitting the Earth, which is how we think the moon was formed, that didn't push the Earth out of its orbit and tilt the orbit. It's a very peculiar effect. I mean, it may be that this star has had an interaction gravitationally at some time in the past and shifted the orbit of the planet by the gravitational interference of something else going past. But that's just conjecture. And the bottom line is, for a single planet going around a star, this is the most peculiar one we've ever found. It's because of this tilt in its orbit.
And that's what we keep seeing. Every time we find something new in another solar system, we find, not every time, but we are starting to find something new and different and unexplainable. And nothing's normal, really, when it comes to all these new discoveries.
That's correct. That's right. It's a universe out there that's full of diversity. That's probably the best way to put it.
Yeah. And quite a strange place. Do we know what kind of planet it is?
It's a super Earth. I think it's got a mass of 39 Earths, so it's something less than Jupiter. But I think it's not as big in diameter as Jupiter is. I think that's right. But it probably means it's a hot Jupiter, basically, or a hot sub-Jupiter. Perhaps that's the best way to put it.
Right. Okay. Well, it's another interesting find. I'm sure they'll keep looking at it to try and figure out how it ended up where it is and why. But yeah, it sounds logic. If you tear it all down, you go with the most obvious answer. It's probably been hit by something. Probably Steve Smith's cricket bat would be my theory.
I think you've probably just baffled 2/3 of our listeners.
It's probably look up Steve Smith cricketer and you'll know what I'm talking about. Been having a great season, absolutely wonderful season. But I won't gloat because I know we're heard in England, and I don't want to. It's not over yet. So if you would like to read up on that story, you can do so at the dailygalaxy.com website, or you can read the paper in the Astronomical Journal, I think it is. Let me just double check that. Yes, it's the Astronomical Journal. Yep. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Now let's take a break from the show to tell you about our sponsor, NordVPN. Now I think we'll all agree that exploring the universe is thrilling, but exploring the internet without protection, that's a black hole you don't want to fall into. Sorry. As a Space Nuts listener, we have an exclusive deal for you so you can stay protected, and that is NordVPN. It's the fastest, most secure way to browse the web. With NordVPN, you get next-level encryption, blazingly fast servers around the world, and zero tracking, so you can stream, shop, or scroll safely. It's the tool I personally trust when we're diving into the internet, and we want to give you peace of mind. I've used it overseas several times. I've used it at home. It works, and it is seamless. Head to nordvpn.com/spacenuts for an exclusive deal just for Space Nuts listeners. Big savings plus 4 months extra, absolutely free. Don't surf the cosmos unshielded. Secure your digital universe today with nordvpn.com/spacenuts, and don't forget their 30-day money-back guarantee. Go to nordvpn.com/spacenuts.
Roger, you're loud and clear here also.
Space Nuts.
Our last story is about one of my favorite things, and that is chewing gum. I grew up on that stuff. I didn't eat food. I just chewed gum ad infinitum. I used to stick it on the bedpost when I went to sleep and start again as soon as I woke up. I was addicted to the stuff, especially the stuff we had called Big Charlie. I don't know if anyone remembers Big Charlie, but it came in a stick about 1 foot long. And good grief, it was amazing. Anyway, I can't find that anymore. The point I'm trying to make is that this is all about a discovery that's been made on the samples of the Bennu asteroid that were returned to Earth in the deserts of Utah a couple of years ago. And they've been sort of looking at it ever since, and they have found something unusual. It's not chewing gum, but it is like chewing gum because it's a kind of a polymer.
Yeah, I'm still grappling with you and your chewing gum on the bedpost. If I remember rightly, it was Lonnie Donegan who in the 1950s had a big hit with "Does Your Chewing Gum Lose Its Flavor in the Bedpost Overnight?"
The answer is yes.
Yeah. So straight from there to Asteroid Bennu. I think it was Lonnie Donegan anyway.
Yeah, I can't remember, but I know the
great skiffle artist of the 1950s.
There's a photo of Big Charlie. I don't know if you can see that. No, you can't.
I can't. No, it's just disappearing because all I can see now is the moon.
Yeah. Anyway,
a Big Charlie. We did
Charlie
those in Britain. Good grief!
Lucky you. On. Yeah, it was a monster packeted. Like you couldn't put it in your pocket. You'd poke an eye out.
Well, I have to say, it's something not at all like that we're talking about with Asteroid Bennu, because all these observations have been made with an electron microscope, which you probably didn't need for a Big Charlie. But what's it all about? It's what's been found in the dust, which was returned by the OSIRIS-REx spacecraft, I think in 2023, if I remember rightly, samples from Asteroid Bennu. It's a NASA project. What has been found in there is what the scientists call nitrogen-rich polymeric sheets, which you and I would call gum. Yeah. It's a polymer, basically. And polymers are materials where you've got these long chains of molecules that give them that sort of flexible and sticky flavor, or not flavor, but demeanor. Let me put it that way. So it's got these long chain molecules on it. And so the scientists are calling it space gum. It's not gum as we would know it, but what they've done is they've found sort of almost like shards of this stuff within the dust samples from Bennu. And in order to analyze it, they've actually had to coat it with a layer of, I think it's platinum, that they've reinforced it with so that they can take samples from it with a tungsten microneedle. And you can see pictures of all this stuff going on the web. The University Today's got a nice story about it. And then with the microneedle, then you can take the samples and, analyze them with all the various pieces of kit that we use to make these analyses. And it turns out, there's gum there. I think the puzzle is how it got there, because, let me just, since we're mentioning Universe Today and their lovely article by Andy Thomas Stwick, I think is his name, might not be how you pronounce it, but what he says is one question remains. How exactly did the space gum survive on Bennu for so long? We know that Bennu was part of a larger asteroid that had hydrothermal vents, meaning the asteroid itself was subjected to water. Complex organic molecules, like the space gum, usually either dissolve or break up when subjected to hot water. So how had this particular sample avoided that fate? And what they're saying then is that perhaps the sample might have formed basically during a phase when Bennu was cold, before it actually got hot enough for nuclear processes to heat it up. And they're saying that these samples actually date from that time, and that basically what they say is by the time radioactive elements inside the asteroid, and this again is quoted from Universe Today, by the time the radioactive elements inside the asteroid had heated up enough to create the water, the plastic, in inverted commas, sheets of polymer were already formed and were in fact water resistant, thereby getting trapped by the rocks on the asteroid's surface, where they were eventually picked up by an intrepid space probe, namely OSIRIS-REx. So and here's the really interesting bit. We've got other asteroid samples, as you know, Andrew, from the two Japanese spacecraft that have brought back asteroid samples. And neither of those have polymers in them. So Bennu's different. It's a different body. It's still a rubble pile asteroid as far as we know, but different in its chemical makeup.
So I suppose that throws up questions about asteroid formation and why this is different, or is it normal and the other two were different? You don't know, do you?
Yeah, that's right. That's the thing. Yes.
Yeah, very interesting indeed. If you'd like to read about it, universetoday.com has that great article that Fred was talking about. And we'll probably learn more and more as they keep going through those samples from Bennu. Fred, we're all done. Thank you so much. That was quick.
It was, wasn't it? And they were quite complex stories as well.
Yeah, that's probably why we didn't spend much time on them.
It could be, yeah.
Our brains.
Neither of us understands them either.
Yeah. All right. Thanks, Fred. We'll catch you shortly for our final program of the year, officially. So we'll see you then. Thanks, Fred.
Sounds great. Well done, Andrew.
And thanks to Hugh in the studio, who couldn't be with us today because of a weird object that he's gone to see the doctor about. And don't forget to visit us online, and you can do that at spacenutspodcast.com or spacenuts.io, and check it all out there. You can go to our supporters page if you would like to learn more about how to support us in whatever way you feel fit. You don't have to. It's not mandatory. Or you can send questions in via the AMA link, sign up for the Astronomy Daily newsfeed. But Christmas is coming up. Don't forget to visit the Space Nuts shop. It's all at spacenutspodcast.com. And from me, Andrew Dunkley, thanks for your company. We will see you again on the next episode real soon.
Space Nuts. You've been listening to the Space Nuts Podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.